Um, let me, I think maybe Tom covered this, maybe not, but it's not going to hurt anything for me to just make the statement here. So suppose that P is a positive prime and R greater than, and N an integer greater than or equal to 1. Then F is a finite field. Order. Again, if and only if F is a splitting field. X e to the n minus x over okay, so let me discuss why this is true. Julie's out there. Okay, so I'll say this right now, also kind of a class fact. Finally, at this late date, I had a grader from this class, which means that I will grade. I've been grading all your stuff, but the grader's graded, I think, your homework 5. It's done. So I'm going to probably grade she'll probably grade most of the stuff from here on out, or maybe we'll kind of split it. But anyway, if there's any questions on the grading, just let me know. So why is this true? Well, notice that the first thing I want you to notice is this is a the first thing that you might be worried about, since we're in characteristic P, is oh dear, could this have multiple roots, which is always kind of a danger in that situation. But not here, because I love this. The derivative of this is -1, right? Because the P to the n kills that first term, get -1. So GCD of F and F prime is 1 and F is 7. Notice that there are P to the n roots. Are P to the n roots. And of course they are distinct. By the fact that it's separable. Okay. Notice that this forms a ring. If, let's say, X and Y, let's say Y and Z are roots of X, then notice that Y to the n equals Y and C to the n equals Z. So This is an inductive application of freshman's dream, or even better, this is the nth power of the Frobenius that Todd probably talked about last time. So the roots form a ring, right? Well, I guess you need negative, but that also follows easily. So the roots form a ring here, and in fact, a field. If y to the p to the n is y, and y is not 0, then y to the p to the n minus 1 is equal to 1. Therefore, y times y to the p to the n minus 2 equals 1. And so, ring the field because all non-zero elements are invertible. So those are the pieces of the puzzle that you need to sort of solidify this right here. Any questions? I'll give you a couple of corollaries. Corollary 866 for any prime and integer n, n greater than or equal 1, there exists a field of order and it's unique up to isomorphism. And I can sort of, I think, satisfy you in one fell swoop on this one right here, because field is splitting field. We know it exists by the theorem, right, that the splitting field is in fact a field and it's got p to the n elements. And the unique up to isomorphism comes from the fact that splitting fields of a polynomial are unique up to k isomorphism, up to z isomorphism in this case. Here's another corollary, which I find this corollary very kind of interesting, because if you try to prove this sort of from basic principles, I think it's not so obvious to me how to do it. But here it follows very nicely. 8.6.7. For any n greater than 1 and finite field F, there exists an irreducible polynomial over F greater than 1. right? I mean, even for ZP, right? So let me give you an example here. Look at quadratics. We'll do this. I'm going to go through this example rather painstakingly. You have x squared, 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 squared. Right. That's it. That's the entire list of all quadratic polynomials over Z2. Right. Now, clearly x squared is not irreducible. And this one is not irreducible because this is x plus 1 quantity squared. Right? This one's not irreducible, it's got factor of x in it. This one has to be irreducible. Notice that if you take F2, then you have omega squared plus omega plus 1 is 0. And then it's say omega squared is omega plus 1. Basically, I can construct the field of 4 elements this way. Remember, back when we first did the field theory in the algebraic business, the way you build this root omega is you take Z2x and you mod out by its minimum polynomial. Notice that this polynomial here is irreducible, right? Because it's quadratic and it has no root, right? That is until we make omega the root. Notice that the field of 4 elements consists of this. It's a vector space of dimension 2 over the field of 2 elements, and you can consider 1 and omega your basis. And you may say, where is omega squared? Well, there it is. It's omega plus 1. So the multiplication table for this, the addition table is pretty straightforward, I think, because it's just mod 2 addition. 1 plus 1 is 0. Omega plus omega 0, 1 plus omega is this plus this is that. It's like a Z2 structure. If I make the multiplication table, of course, getting rid of 0 because 0 gets trivial multiplication, I get one omega plus 1, omega plus 1. Omega squared is omega plus 1. Omega times omega plus 1 is omega squared plus omega. And omega squared plus omega is 1. And omega plus 1 quantity squared is omega squared plus 1, which is omega. And there's what the field of 4 elements looks like multiplicative. Now, let's do one more over Z2. And I do this over Z2 because it's easy to form the polynomials, but obviously you can do this over any field. What about cubics? Let's see what we get here. There should be 8 of them. Now, the first thing I'm gonna do is I'm gonna mark out the ones that are reducible, right? That's reducible. Notice that one is a root of this, so this is reducible. And basically, cubics are easier than quartics because you don't have to check for irreducible quadratic factors. If you have a quadratic or a cubic, if it reduces, it has to have a linear factor. So you can check the roots, that makes it life easier. Obviously, this one, anything that's got a zero constant term is reducible. So all of these are reducible. Notice this one's also reducible because when you plug in one, you get zero. And this leaves two here. Both of these are irreducible, right? Because when I plug in zero, I get one. And when I plug in one, I get one. And the same thing here. Question? Yes.
Do we have anything that says, so we have that there exists an irreducible polynomial? Do we have anything that says how many of them there are for over certain fields?
Right, because
So like we had one there and then we have two here.
I feel fairly confident in saying that somebody that does this kind of computational stuff might figure this out. But actually, we may be able to recover your answer in a moment. Let's see. Now, let me point out a couple of things in this example that I used to illustrate. On the one hand, if you look at the first example for the quadratic case, then this is Z2 adjoined with a root of this quadratic polynomial. But also, we just had a theorem that says that this field here, F4, is the splitting field of right? Isn't that what the theorem said? Right? It's a splitting field of this. Well, let's see what happens, shall we? And actually, I'm going to replace the minus with a plus, so I don't have to worry about it. Because remember, I'm in characteristic 2 for this example, so plus and minus, there's no distinction. Now, notice this piece. Notice by the proof of that previous theorem, this has to have 4 distinct roots, and it needs to be those here. Notice one of them is 0. This one has a root of 1, and notice now, let's see what happens here. Because, as you pointed out, you've got 2 polynomials here. Now let's see what happens. So I didn't bother to put the multiplication table out here because it would be like, 7 by 7 if I took the 0 out. But you could certainly do it by the same sort of techniques that we did here. Let's see what happens with polynomial. Again, I have 1 as a root of this. So this is x times x plus 1 times, well, let's see what we got here. X7, everything cancels in the middle, like an accordion, down to 1. Now, nobody wants to muck around and try to reduce this, does it? But let me just take a flyer. I want to guess this.
It's gonna be
I will bet lots of money, this is what it works out to be. What happens here? X6. How do I get an X5 out of this? Only this way, so there's one X5. How do I get an X4 out of this? Let's see. Did I do this? Oh, no.
your middle X and your X.
Right, so how do I get an X4 out of this? There's X time, there's an X4, and I guess that's the only way. So there's your X4. How do I get an X3? It looks like there's three ways to do this. X cubed, X cubed, X cubed. 3x cubed is 1x cubed. How do I get an X squared? Only one way, that way. How do I get an X? Only one way. How do I get one? Amazing, right? And so basically what this tells is polynomials are the same, but the roots give isomorphic extensions, actually, right? Notice that this extension is degree 3 over C2. So 8 elements. And so it turns out that, of course, if you take Z2 and join a root of this, in there somewhere you will get a root of this. Okay, any questions on that? Okay, I'm going to give you a last, and actually we're going to talk more generally about this. These are special cases. Sometimes the finite fields are called Galois fields. And the reason for that basically comes from this last theorem here. Theorem H6a. If K is a finite field and F is a finite extension, and F is a finite extension, I think degree n, then F is finite and Galois over K. And I got the Galois over cyclic. The generator of the Galois group of F over K is the CR Frobenius. Well, I should say power. of Frobenius. So this is why they're called Galois fields, because there are, notice every one of these splitting field of a set of polynomials over the smaller one, the degree of the extension in the Galois group is a degree n, where n is the degree of the extension. So, but let me point out something that, so a little bit of care is to be taken. Notice that so notice that, for example, F 16. F16 is Galois over F4 and F2. Right? The degree is 2. Right? And the degree of 16 F2 is so the Galois group of F16 over F2 is Z4. This one is Z2, right? But F16 and F8 are not comparable. Because this is a degree 3 extension of Z2, and this is a degree 4 extension. So if I were to draw a little lattice of these fields here, what you would have is F2. That's a degree 2 extension. This is a degree 3 extension. And this is a degree 2 extension. So the total degree of extension here is 4, right? But these two aren't comparable. Now, of course, you can find a big enough field that both of these fit in, right? But you've got to go up further. Okay. Any questions on that? Okay. Questions? Okay, so let's let me get into this here. We'll get started on this anyway. Okay, so here's some approaches to finding the Galois group. So I want to tell you the main tools in my own little toolbox, other than getting on some software and typing it in. How would you do this, assuming that, you know, somebody just set off an AMP and we could do all that stuff? I'm going to usually do Galois group over Q, which will be specific to the first bit, but you can generalize it for later stuff. This will mostly be small degree stuff, but I'm going to give you a general result that allows you to do things, and I'll show you kind of a trick that allows you to narrow down things. And I'll give you kind of a popular story. Proposition 851. Let f of x be I'm gonna also do most of this, not all of it, most of it without proof. The proofs for most of this are not too difficult, but some of them are kind of computationally messy, and I'm gonna at least probably talk you through it a little bit. Let f of x be separable and irreducible of degree n. This theorem I've actually given you before, but I'll talk about it a little bit more now. The splitting field. Oh, and by the way, when I say the Galois group of polynomial, what I mean by that is we're assuming that we've got some fixed base field. And what I mean is the Galois group, I'm assuming the polynomial is separable. And what I mean by the Galois group polynomial is the Galois group of the field generator, the splitting field of the polynomial. The splitting field f of f of x over k is Galois because it's normal and we're assuming the polynomial is separable of degree less than or equal to n factorial. Right, that's a theorem that we have from class already. There's nothing new here. What is more, n divides the order of the Galois group of f over k. And the Galois group of f over k is a transitive set. And the fact that it's transitive, we discussed a little bit before. If it's an irreducible polynomial with two roots u and v, then there's an automorphism of the splitting field that takes u to v, and that's why it has to be transitive. So if you list the roots, there's n of it. Then given any two roots, there's an automorphism that takes one to the other, which is exactly what it means to be transitive. So let me give you some perspective here. Example. So let's look at transitive subgroups of these various SNs, isomorphism classes. There's only two subgroups of S2, because S2 just consists of the identity and the permutation 1, 2. The identity is clearly intransitive, so only S2 is transitive. There are 6 subgroups of S3. One of them is the identity. The alternating group of on 3 letters is transitive because remember, any 3 cycle is in AN, right? Because 3 cycles are always even. And so to make it transitive, suppose you want to take I to J, just take IJ and just put the 3rd letter or any other letter there, and you've got it. So AN is always transitive, SN is. None of the subgroups of order 2 are transitive because they consist of just transpositions, so there's always something left out. For S4, for exactly the reasons that we described before, S4 and A4 are always transitive subgroups. Notice anything with a 4 cycle in it is transitive. So C4, D4. So C4 is cyclic of order 4. D4 is the dihedral group on the square. And this group I'm going to call V, I'm going to use this in the notation later. It consists of E, 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. This particular, notice that this group is isomorphic to the Klein 4 group. This is isomorphic to Z2, Z2. It's not even clear it's a group, right? You actually have to do the computation to multiply this by this and see that you in fact do get this. But this is actually a group. And once you believe it, it's got 4 elements. Every non-identity element is order 2, so it's isomorphic to Z2, Z2. And once you believe it's a group, it's pretty easy to see it's transitive, right? Because there's how you get 1 to 2, there's how you get 1 to 3, 1 to 4. Let's see, also need to get 2 to 3, we need to get 2 to 4, and we need to get 3. So there you go. And that's it, actually, for S4. There's also, there's 5 here as well. S5, A5, cyclic order 5. It's pretty easy to see, actually, that any end cycle is going to be transitive. Or it's going to, if you have an end cycle, you get transitive through. D5, and this weird, there's a subgroup of, this is called the Frobenius group of order 20. It's a subgroup of order 20 in S5. And I know why it's transitive, because I know enough group theory now, because if you've got a subgroup of S5 of order 20, then that subgroup of order 20 has to contain an element of order 5 by Cauchy's theorem. And if it's an element of S5 of order 5, it has to be a 5 cycle. So anything, if it's got order 20, it has to be transitive. And it turns out that up isomorphism is a complete list as well. But don't hold out. By the way, you can generate that with F20 with cycle 1, 2, 3, 4, 5, and 1, 2, 4, 3, for example. Now, do not hold out any great hope that I'm going to list much more of this, because let me point out that S7 has 7 transitive subgroups. And here again, I mean isomorphism class stuff. And I bet you can guess a few of them yourself, right? I mean, you should be able to rip 4 of them off this one, because it should be S7, A7, cyclic order 7, and dihedral on the heptagon or septagon, whichever you want to call it. And then there's a couple others. But S6, there's 16. And just to give you some perspective, S8, there are 50. And S12, 301. Right, nobody wants to be listing that. So in other words, if you have a 12th degree polynomial, there's a lot of possibilities for the Galois group. So we're gonna at least take a flyer at doing some of these low degree polynomials. I'm gonna show you how to get the Galois group for any polynomial up to degree 4 over the rationals. Up to and including degree 4. And then I'll show you how to compute Galois groups more generally. Definition. So we're going to define something called the discriminator, and this is an incredibly important tool for figuring out Galois groups. And I'm not going to formally prove it, but I'm going to explain why this works. Let f of x mean k of x, and I want the characteristic of k to copy 2. Suppose that n is of the degree of f. And that f has n distinct roots. In splitting field. We define delta well, let me add this here. Yeah, Ri are the roots then we define this thing delta to be equal to the product I less than j of Ri minus Rj. The discriminant is equal to delta squared. Okay, so let me give you an example here. Let me kind of an example. No. Well, actually, suppose I have this polynomial here, and let's just kind of do this blind. The roots are -b plus the square root. Two is -b minus square root. Agree? So delta is well, if we call this R1, so I less j, the only thing we can do is just subtract these two, that's it. And so this is R1 minus R2, which is going to be B squared minus 4AC over A. Right. And so the discriminant here is that. Now notice, you all are probably used to back in the days in high school or whatever, if you remember back then, they usually called the B squared minus 4AC the discriminant, right? But that's okay because it varies from the D that you learned in high school by square in the rationals. So proposition. Say 4. The first thing that I want to observe is that D is actually in K. And delta is in K. Also, delta is in K. If and only if the Galois group of the splitting field of F over K is obtained. Okay. Okay, so let's see if we can kind of discern why this is true. Well, I guess I better just write this too complicated. Oops. Okay, can somebody explain why D must actually be the square of the discriminant, if you will, must be an element in K? Notice it worked out this way, didn't it? Because the square of the discriminant in the quadratic case is a quotient of these two rational numbers, so it's still a rational number. Notice what happens when you apply any element of the Galois group, that is any automorphism to D. What does it do? It permutes these roots, right? But these are all distinct roots. And so the only thing you can do is maybe, I mean, yes, Ri may go somewhere else and Rj goes somewhere else, but basically you get the same product, except some of these might be turned around. But if you square it, it doesn't matter if you turn it around or not. So when you apply anything here, all it does is takes each Ri and Rj and permutes it to a product, it's the same length product of differences in roots. It's just sometimes it might not be the case anymore with i's less than j, but since you're squaring everything, it doesn't matter, right? So equal V for all sigma in the Galois group. Therefore, V is in K because it's the fixed field. Okay. What about this other remark about that actually the original delta is in K if and only if the Galois group is contained in AN? Let me give you an example that you can generalize. Remember, what it means to be in AN is it means the permutation is even, which means that basically you're flipping an even number of these, right? Which means that in the case that it's an even permutation, you preserve the sign, right? And so if you do an even permutation to this, it will, so sigma and that's essentially why this works. See if you can work through that. We've kind of run out of time for today, but think about that. Think about that for next time, and we'll keep moving. Any questions? Any questions? All right. Well, for any questions, y'all have a good one, and we will see you on Wednesday. Yes, I agree. It's a cool result.